Hello. Today we're going to discuss a very important topic, curve fitting. In fact, we need to study a special method in curve fitting, which is called the least square method in curve fitting. Before going into the details of this least square method, let's see what is meant by curve fitting. In experiments, we come across problems involving two variables. An example is given here as that of a ship, where the speed of the ship varies with the horsepower of the engine. And the formula is P equal to A plus B V cube, where P is the power of the engine and V is the velocity. A and B are constants. And these constants has to be determined if you want to plot a graph between the pressure and velocity. For that purpose, we need to take a large number of readings of the speeds as well as the horsepowers. Like when you're giving the 1000 horsepower, what is the speed? When you're giving 1500 horsepower, what is the speed? And so on. So the problem essentially involves finding the best values of velocity and pressure according to this particular equation. Or this is a general problem to find a suitable relation between two variables x and y from a given set of observed values xi and yi, where I runs from 1 to n observations. And this relation is usually known as an empirical law. And the process of finding such an equation is called fitting the best curve, or we are finding the curve of best fit. And this process is called curve fitting. There are many methods of curve fitting, like a graphical method is there, group average method is there, the method of moments is there, and we have the least square method of which we are interested. And the least square method is supposed to be the best fit of all these methods. So we are discussing that in detail. As in the previous cases that we have discussed in the case of interpolation, let's assume that we have, say, n set of observations, x1, y1, x2, y2, etc., xn, yn, where x is the independent variable and y is the dependent variable. And y is a function of x. This is a relationship between x and y. When x is x1, the corresponding y value is y1. And the expected value from this equation 1 is f of x1. Then there is a probability of a deviation from the expected result. This deviation is called the residual. And the residual of the first observation is E1 equal to y1 minus f of x1. Likewise, you can have n residuals, E2 equal to y2 minus f of x2, E3 equal to y3 minus f of x3, etc. En equal to yn minus f of xn. Some residuals may be positive, some other may be negative, some are even zero. So in order to get equal importance to the positive as well as the negative residuals, we take the squares of all the residuals rather than taking the individual residuals as such. We take the squares of the residuals and add them together rather than adding the individual residuals as such. So such an addition is shown here, where the sum of the squares of the residuals is represented by the letter capital E equal to E1 square plus E2 square plus E3 square plus etc. plus En square, which is y1 minus f of x1 the whole square plus y2 minus f of x2 the whole square plus etc. Finally, the last term yn minus f of xn the whole square. This is equation 2, and this equation 2 is very important. You should remember this equation. So this particular quantity E, this is a measure of how well the curve y equal to f of x fits to the given set of observations. If E is more, that means the curve fits properly to the observation. And if E is large, it does not fit that good. So our aim is to make this E a minimum. That is the essential procedure that we adopt in the least square curve fitting. That's written here. The value of E decreases depending on the closeness of the observed data to the curve assumed. Hence, the best representative curve to the given set of observation is the one for which E, which is the sum of squares of the residuals, is a minimum. That's what we have discussed just now. And this concept is called the principle of least square. So the aim of the least square curve fitting procedure is to make the sum of the squares of the residuals to be a minimum. So we have a data given here. It is a scattered data. We can fit any curve to this data. In the second figure, a line is fitted where the line is taken from the equation y is a constant, right? You can see the red line, it's a hypothesized model. And the blue lines show the distance between the data and the model adopted. And you can see that we have a larger distances between the hypothesized model and the data point. Then we can fit a straight line to the above data, as in the third figure, and we see that that is somewhat convincing, as the distance from the observed points, distance from the data points are somewhat equally arranged. So this is the essential point in least square curve fitting. Of the two figures, the last figure is a better fit because the sum of the squares of the residuals will be minimum in the third figure. At first, we are going to fit a straight line to the given data point, and we know that the straight line has the equation y equal to ax plus b, where a and b are constants. So the essential problem is to find minimum values for a and b. And we are defining a quantity which is called the absolute deviation, which is the modulus of the deviation and predicted value. Yi is the actual point, and axi plus b is the point which is predicted by the equation y equal to ax plus b when the value is xi. And you can add all those differences. The difference between yi and axi plus b taken for n points can be added together, and that sum is called the absolute deviation. Here we are taking the modulus of the deviation. So to minimize a function of two variables, we need to go for partial differentiation, and the partial derivatives should be equated to 0. So the equations become dou s by dou a equal to 0 and dou s by dou b equal to 0. But the problem concerned with this equation is that the absolute value function is not differentiable at 0, and we may not be able to find solutions to this pair of equations. So to solve this mystery, the least square method is proposed. What we do is we are going to determine the best approximating line with the error involved is the sum of the squares of the differences between the y values of the approximating line and the given y values. As we have seen earlier, x1, y1, x2, y2, x3, y3, etc. x and yn be the set of n observations, and we want to fit a straight line to this set of observations. The equation is y equal to ax plus b. What we do is we will write the residuals. The general form of the residual will be ei equal to yi minus axi plus b, where yi is the actual value which is observed when the x value was xi, and axi plus b is the predicted value with the equation ax plus b, and we'll find the values from 1 to n. So we'll find n residuals here. Sum of the squares of all these residuals will be calculated like this: sigma I equal to 1 to n yi minus axi plus b the whole square. And this particular term e has to be differentiated. In fact, we have to take the partial derivative of this e with respect to a and b and equate them to 0 so as to find the values of a and b. So that is the essential technique. So dou e by dou a equal to 0 and dou e by dou b equal to 0. That is when we get a minimum value for E. So the first condition, dou E by dou A equal to 0. When you solve equation 2, we get it as 2x1 into y1 minus ax1 minus b plus 2x2 into y2 minus ax2 minus b plus etc. Plus etc. Last term 2xn into yn minus axn minus b equal to 0. And this solves to be sigma I equal to 1 to n xi square into a plus sigma I equal to 1 to n xi into b equal to sigma I equal to 1 to n xi yi. From the above equation, we are getting this result. Likewise, we can take the partial derivative of e with respect to b, and we get this as the result: y1 minus ax1 minus b plus y2 minus ax2 minus b plus etc. plus the last term yn minus axn minus b equal to 0. From this equation, we can take the general form as a into sigma I equal to 1 to n xi plus nb equal to sigma I equal to 1 to n yi. From these two equations, we can find the values of a and b. These are two equations and we have two unknowns a and b. The two unknowns can be easily calculated. And using a and b, we can write the equation y equal to ax. So we'll see an example here. This is the example. Using the method of least squares, find the straight line y equal to ax plus b that fits the following data. The x values and y values are given. X values are 0.5, 1, 1.5, 2, 2.5, and 3. And y values are 15, 17, 19, 14, 10, and 7. We have the normal equations. A sigma I equal to 1 to n xi square plus b sigma I equal to 1 to n xi equal to sigma I equal to 1 to n xi yi. And a sigma I equal to 1 to n xi plus nb equal to sigma yi. Here, n is 1, 2, 3, 4, 5, and 6. We make a table of values x, y, xy, and x square. We calculate sigma xi, sigma yi, sigma xi yi, and sigma xi square, and substitute these values in equations 1 and 2. We get this is 22.75a, which is sigma xi square into a, plus 10.5b sigma xi into b equal to 127, which is sigma xi yi. From the second equation, a into sigma xi is a into 10.5 plus nb. N is 6. So 6b becomes sigma yi, and sigma yi is nothing but 82. So solving these two equations, we get the values of a and b as a equal to minus 3.7714 and b 20.2667. So we have the equation of y equal to ax plus b, and it is y equal to minus 3.7714x plus 20.667. This is how we fit a straight line to a set of data which is given.